All right, starting with Section ACE overview. This chapter covers what materials are used in the dental lab, like their job to handle, and to store them to preserve properties. Knowing the right way to use and store material good results, it's key. All right, starting with Section 2A, Overview. 2.1 Introduction. This chapter describes the composition, properties, and use of materials in a dental laboratory. Information on the use of these materials is also discussed in chapters dealing with specific laboratory procedures. 2.2 Knowledge of dental materials. Almost all dental materials are obtained from commercial manufacturers. Each manufacturer provides recommendations for handling and storage so that consistent results are obtained. A dental laboratory technician must know which material is needed, how it is handled, how it reacts, and how it is stored to maintain its physical properties. Knowledge of materials is necessary not only to routinely perform tasks successfully, but also to evaluate any failures so they are not repeated. A failure means wasted laboratory time, additional clinic time, and physical discomfort for the patient. Section 2B, Gypsum Materials. 2.3 Introduction. Gypsum is the common name for calcium sulfate dihydrate. Gypsum products are used more than any other group of compounds in laboratory procedures. Manufacturing variations produce plaster, dental stone, dye stone, casting investment, and soldering investment. Each is a formulated powder with specific physical properties. When mixed with the correct amount of water, it forms a fluid paste that hardens into a solid. In the fluid state, it can be poured or shaped as needed. As gypsum sets, dense crystals form and heat is released. This heat release, called an exothermic reaction, occurs as all gypsum products set. 2.4 Physical properties. The main physical properties of gypsum materials include crushing strength, setting time, and setting expansion. Crushing strength or compressive strength is the greatest compressive force a material can withstand before fracturing. The strength of gypsum increases rapidly as it hardens. Because water content affects strength, two types are recognized: wet and dry. Wet strength is measured with excess water still present. Dry strength is measured after the specimen has dried. About 24 hours after setting, a dried specimen has roughly twice its original wet strength. Setting time is the period required for the material to harden. It includes the initial set, when the material is firm enough to remove and trim, and the final set, when crystallization is complete and the heat has dissipated. At this stage, the material has about half of its ultimate crushing strength. If you'd like me to continue in the same style, just say so. Okay, picking up where we left off. Table 2.1 shows plaster. Initial set in 7 to 13 minutes, final set around 45 minutes. Stone or hydrocal. Initial set 8 to 15 minutes, final about 45 minutes. Dye stone. Initial set 15 minutes, final 25 to 30 minutes. Soldering investments. Initial set 8 to 12 minutes, final 18 to 22. Their heat resistance and expansion match the solder and metals used. Gold casting investments. Initial set around 12 minutes, final 35 to 45. Expansion must offset roughly 1.4% gold shrinkage. For chrome nickel titanium investments, initial set 8 to 12 minutes, final about 20. Expansion must cover about 1.7% shrinkage. Setting expansion is the slight volume increase as gypsum hardens, generally a fraction of a percent. Normal expansion occurs in air. Hygroscopic expansion happens when setting underwater and is typically more than double normal. Semi-hygroscopic expansion comes from limited water contact. Thermal expansion occurs when heated, amounts rise with temperature. As for variables affecting strength, more water lowers strength due to increased porosity. Up to 1 minute of thorough mechanical mixing can increase strength, but overmixing weakens it. Chemical modifiers usually reduce strength, though borax can increase surface hardness. Setting time is also affected. More water means longer set, less water shorter. Warmer water between 32 and 85 degrees shortens setting time. Temperatures from 85 to 120 degrees lengthen it, and at boiling, gypsum will not set. 2.6 mixing. The setting time shortens as the mix is spatulated longer or faster. Accelerators and retarders are sometimes used. An accelerator shortens setting time. A retarder lengthens it. Manufacturers use them to standardize products. They may also be used to modify normal set. Potassium sulfate and table salt are accelerators. Vinegar, potassium citrate, and borax are retarders. However, these chemicals also reduce setting expansion and strike. So never use them with casting or soldering investments. Adjust water temperature and mixing instead. One acceptable exception is slurry water for mounting casts, a concentrated suspension of gypsum particles that greatly accelerates set. 2.7. Manufacturers control setting expansion with modifiers and exact proportions. Thick mixes with less water and longer mixing times both increase expansion, and vice versa. 2.8. Modeling plaster is made by grinding gypsum and driving off water of hydration. Dental plasters are manufactured for consistent working properties. ANSI/ADA specification number 25 sets a maximum setting expansion of 0.3%. Okay, continuing uses of model plaster. It's used for matrices, flasking dentures, mounting casts, and in some investments. Initial set is 4 to 12 minutes, final 20 to 45. Impression plaster is designed to set faster and be weak and brittle for removal. It's now largely replaced, has very low expansion, around 0.13%, and today is used mostly for bite registrations and solder indexes. Dental stone is stronger and denser than plaster, used for casts, and has about 0.12% expansion. Die stone is harder and more dense again, used for crowns and inlays with expansion from 0.08 to 0.18%. A strict water to powder ratio is essential for accuracy. Next, we move into investment materials. Sure. Picking up there. Section 2.12 Investment Materials. Investment materials form molds for molten metal and relate pieces for soldering. They consist of a refractory material such as cristobalite or quartz and a binder, gypsum, phosphate, or silicate. High cristobalite content yields more expansion. High quartz yields less. Gypsum-bound types release sulfur dioxide if overheated, so burnout should stay below 1300 degrees Fahrenheit and casting below 1950. Titanium's gypsum investment is an exception, tolerating 1350-degree burnout and 2600-degree casting. Phosphate and silicate binders withstand higher temperatures. Inlay investments are usually gypsum-bound. Gold shrinks about 1.4% on cooling, so the mold must be expanded to compensate. This is done by thermal or hygroscopic expansion. High heat techniques use burnout above 1300 degrees Fahrenheit. Low heat use 1300 or less, often with a hygroscopic method to gain extra expansion. All right, continuing. Section 2.14 Soldering Investment. It uses quartz and has minimal expansion, so it's not for casting. It may be gypsum or high heat bound. Above 1950 degrees Fahrenheit, use a high heat binder. Section 2.15 for chrome alloys. High heat investments use quartz with ethyl silicate for alloys melting at 2700 to 2800 degrees Fahrenheit. Low heat types are gypsum bound for titanium frameworks. Titanium shrinks about 1.7%. Sulfur dioxide liberation is a serious problem, so handle it exactly as directed. Section 2.16 Investments for ceramic gold alloys. Gypsum bonded investments aren't satisfactory for these alloys. Magnesium oxide and soluble phosphate based investments are used instead. 2.17 Handling gypsum materials. Rule 1 Keep everything clean. Rule 2 Tumble contents before using. Rule 3 Add powder to water, not water to powder. Rule 4 Always measure water and weigh powder accurately. Rule 5 Mix well but don't whip air into the mix. For phosphate bonded investments, vacuum mix to remove gas from the mass. Rule 6, never add to a mix. Rule 7, use good equipment that is clean and accurate. Rule 8, avoid contamination. Rule 9, know your material, including batch number and expiration date. Section 2.18, storage of gypsum materials. Gypsum products for dentistry are manufactured to rigid specifications. Exposure to air for extended periods can seriously alter their working qualities. Setting time may change, setting expansion may change, and crushing strength is likely to drop. The user has no way to know how much, if any, of these changes have occurred. So, gypsum materials should be stored in a dry room, preferably in sealed containers. Also, use the oldest material first, rotating stock. Heavy constituents may settle out in investments, so always tumble before using. Section 2.19, proper handling of plaster and dental stone casts. 2.19.1, effect of water. Dental stone casts erode in water. Erosion starts immediately upon exposure. How rapidly it proceeds depends on the mineral content and temperature of the water and the density of the stone. Under no circumstances should stone casts be submerged in tap water. 0.19.2, saturated calcium sulfate dihydrate solution, or SDS. SDS is made by adding small amounts of plaster to a container of water until no more will dissolve, a saturated solution. SDS can also be made with dental stone or gypsum-bound investment. SDS won't erode the cast surface like tap water does. It's very useful for quick wetting or cleaning of casts. Section 2.19.3, wetting a cast during laboratory procedures. If slurry builds up, rinse with a liberal amount of SDS. If you need to moisten the cast during a procedure, avoid submerging it. Place it on its end in an SDS bath. Don't allow the SDS level to reach the occlusal surface. Air in the cast will slowly work itself out. If submerged, bubbles rise through the cast and can lift off relief wax. Section 2.19.3.4, and that's where the provided text ends. From section 2.19.3, wetting continues slowly from the base toward the tips of the teeth. This is very similar to the wick action of a kerosene lamp. If relief wax is present, escaping air can lift the wax off the cast. Place the cast on end, not on its base. And that's the end of Chapter 2, Dental Materials. If you want a super quick review of the high yield points for CDT, here you go. Gypsum is calcium sulfate dihydrate. Dry strength is about twice wet strength after about 24 hours. Initial set means you can remove and trim. Final set is full crystallization. More water, lower strength, and increases setting time. Less water increases strength and expansion. Mix up to a minute for strength, but over-mixing weakens it. Accelerators are potassium sulfate and table salt. Retarders are vinegar, potassium citrate, and borax. Never use accelerators or retarders in casting or soldering investments. Slurry water is an okay accelerator for mounting casts. Model plaster expansion runs 0.2 to 0.3%. Impression plaster is around 0.13%, dental stone around 0.12%, dye stone between 0.08 and 0.18%. Gold shrinks around 1.4%, titanium chrome alloy about 1.7%. Keep gypsum bonded investments below 1300 degrees Fahrenheit burnout and 1950 degrees Fahrenheit casting, except the special titanium system. Always add powder to water, never the reverse. Use distilled water, clean equipment, exact water-powder ratios, and never add to a mix. Sewer gypsum products sealed and dry. Rotate stock and tumble investments before use. Don't soak stone casts in tap water. Use SDS when you need to wet them. That wraps the text you provided. If you send the next chapter, I can keep going in the same style. Okay. Right. Picking up with Section 2C, dental waxes. 2.20, general information. Dental waxes are blends of natural or synthetic waxes chosen to produce specific properties for different procedures. Melting point, stickiness, and color can all be modified with additives. They come in lots of forms, sizes, and colors. And because formulations vary, you really have to get a feel for each type you use. Table 2.2 lists the common ones. Base plate wax is used for denture wax ups and filling the tongue space on lower impressions. It comes in medium and hard, usually around 1 millimeter thick. Inlay wax is for patterns like inlays, onlays, crowns, pontics, and RPD frameworks. It's the most accuracy critical wax and comes in medium and hard types. Ivory or white wax is basically non-pigmented inlay wax for acrylic jacket crowns. Lax forms include sprues and preforms for RPDs. Sheet casting wax provides relief under RPD retention grids in 24 to 30 gauge thicknesses. Sticky wax holds broken pieces together before pouring an index. It snaps cleanly at room temperature. Utility wax is for beading impressions and is tacky at room temperature. Boxing wax is used to dam up impressions for pouring. Blockout wax eliminates unwanted undercuts in RPD work. It flows, sticks, and cuts cleanly. Beeswax seals refractory casts and is usually applied around 290 degrees Fahrenheit. Section 2.21 Groups of waxes. Impression, pattern, and processing. Impression waxes are mainly for the dentist. They melt easily, flow at mouth temperature, and distort easily. Examples are corrective and jaw relation recording waxes. Pattern waxes are used by both dentist and lab tech to make patterns. And that's where we'll pick up next with the different pattern waxes, starting with base plate wax in section 2.22. Send it when you're ready. Picking up where we left off. Section 2.22, base plate wax. It's made mainly of beeswax, paraffin, and coloring. The ingredients are fused, cast into blocks, and rolled into sheets. A typical formula is 50 parts yellow beeswax, 6 parts gum mastic, 3 parts prepared chalk, and 4 parts vermilion. Requirements. It needs to be fairly hard at mouth temperature under bite pressure, hold teeth in place without becoming brittle, and stay uniform across room and mouth temperatures. Types include hard and medium. Hard is for warm climates but may crack in the cold. Medium is for cooler climates but can flow too easily in heat. Uses include occlusion rims, boxing matrices, filling the tongue space in lower impressions, denture wax-ups, and so on. Most sheets are about 1 millimeter thick. Inlay wax is next. It's mainly paraffin for body, gum dammer for smoothness to reduce flaking, and carnauba to control hardness and softening points. Requirements are strict. It must capture fine detail, carve without chipping, be workable both at mouth and room temperatures, stay dimensionally stable across temperature changes, resist breakage in thin areas during investing, and burn out cleanly without residue. There are 3 types. Type A is hard, low flow for indirect techniques. Type B is for direct patterns in the mouth. Type C is for indirect lab work. Ivory or white wax is simply unpigmented inlay wax, handy for acrylic jacket crown patterns, since it won't stain the acrylic. Next up is section 2.25, casting waxes for partial dentures, including preforms, sheet casting wax, sticky, utility, boxing, blockout, disclosing wax, and beeswax. Just send the next chunk when you're ready. Okay, picking up where we left off. Section 2.25, casting waxes for partial dentures. Freeformed wax comes in various shapes and sizes for RPD frameworks, and round wire wax can double as sprues for fixed prostheses. Inlay wax is used to flow and carve joints between preformed pieces when making RPD frameworks, and also for spruing patterns. Sheet casting wax is very similar to base plate wax. At room temperature, it's tough, pliable, and tacky, so it sticks to the cast. It comes in 24, 26, 28, and 30 gauge. Smaller number means thicker wax. Main use is to relieve the ridge on an RPD master cast, and it's often used with base plate wax for a uniform denture palette. Sticky wax is beeswax, paraffin, and natural resin. Resin makes it hard and sticky. Key feature, it breaks instead of bends under pressure. Great for holding broken denture parts or wrought wire clasps before investing for soldering. Utility wax is very pliable, comes in ropes, and is tacky at room temperature, so no heat's needed. Main use is beading impressions before boxing or building up tray borders before pouring casts.
Boxing wax strips are about 1.5 inches wide and 12 inches long, used to box impressions. It's pliable at room temperature. Low fusing impression wax is softened in a water bath and painted on tray tissue sides for corrective impressions. Handle gently, don't touch the tissue surface, and rinse carefully. No separating medium is needed before pouring. That catches us up to the end of 2.29. Send the next part when ready, and I'll carry on. Picking up where we left off. Section 2.30, Undercut Wax. Undercut wax, also known as blockout wax, is formulated so it can be built up around an abutment tooth and carved cleanly with a surveyor. It's typically a mix of beeswax, resin, and kaolin and comes in little jars. 2.31, Disclosing wax. Disclosing wax has a very low fusing temperature and flows readily under pressure. It's used to reveal high spots when seeding cast restorations. Laboratory wax. The wax is melted onto the tissue side of the casting, and the restoration is pressed into place. Wherever the wax is displaced, that's where you relieve. Beeswax in cakes or bars is used molten to seal refractory casts. Heat and fully dehydrate the cast first to avoid cracking. Dipping seals the cast, smooths the surface for attaching wax or plastic patterns, and helps prevent moisture absorption during investing. Now into section 2D, impression materials. 2.33, Introduction. Many materials are used for impressions because different procedures demand different properties. Complete denture impressions must capture all tissue. Partials need both teeth and soft tissue undercuts. Often, 2 or 3 materials are combined to get the benefits of each. Table 2.4 summarizes the main impression materials. Modeling plastic is used for preliminary and final complete denture impressions and custom trays. It's firm at room temperature but distorts with heat. Low fusing impression wax is for specialized impressions, easily distorted by heat and pressure, so handle gently. Zinc oxide eugenol paste is for final complete denture impressions. Jaw relations, base plate stabilization, very stable but rigid. Rubber-based polysulfide is for complete dentures and fixed prosthetics. Accurate, durable, elastic, can be poured twice, stains clothing permanently. Reversible hydrocolloid, agar, is for RPD and fixed impressions. A tough type is used for cast duplication. It's pleasant to use, but not very stable dimensionally and must be poured immediately. Irreversible hydrocolloid is used for RPD and other impressions. It's easy and pleasant to use. Silicone impression material is used for fixed prosthetics. It's very accurate and easy to use, but expensive. Section 2.34, Modeling plastic. Modeling plastic is a mixture of resins, waxes, and shellac. It softens in hot water, hardens at mouth temperature, and is used for preliminary and final complete denture impressions and for custom trays. It can be corrected by adding more compound. Impression compound is a thermoplastic mixture of shellac, stearic acid, gutta percha, and filler. It's a poor conductor of heat and becomes plastic at around 140 degrees Fahrenheit, hardening again around 115 degrees Fahrenheit. It should be softened in water and not over a flame. Modeling plastic or compound is available in sheet, stick, and cake forms. Section 2.34 goes into the specific types and their uses and handling. For sheet form, it's used for impressions over full dentures. It's softened in a water bath or over a flame, then adapted to the tissue side of the stock tray, tempered in hot water, and placed in the mouth. The mouth chill hardens the compound. The material should not be forced or muscle trimmed while it is too soft. It can also be corrected by adding more compound if necessary for the stick form. The stick form is used to correct or modify sheet compound impressions or to make a border on a special tray. It is softened in a flame, tempered in water, and placed in the mouth. The mouth hardens the compound. The material should not be forced or muscle trimmed while too soft either. For the cake form is used for making custom trays or for copper band impressions. The compound is softened in a water bath or over a flame. As with the other forms, it should not be forced or muscle trimmed when too soft. Section 2.34.4 Corrective Impression Wax. Corrective impression wax is used for very specialized impressions. It's a low fusing paraffin mixture that's softened in a water bath in a copper band. Handle it very gently and don't touch the tissue side. No separator is needed for pouring. Section 2.35 Zinc Oxide and Eugenol Impression Paste. Zinc oxide eugenol impression paste consists of 2 tubes of paste. It's used for final impressions of complete dentures, jaw relation records, and base plate stabilization. When the two pastes are mixed, they set to a rigid mass. The material doesn't distort and is dimensionally stable. Section 2.36 is on rubber base materials. Rubber base impression material is supplied as a base and a catalyst. It's accurate, durable, and has good elastic properties. It's not very pleasant to work with and will permanently stain clothing. It's used for complete dentures and fixed prosthetics. Section 2.37 covers hydrocolloids. Hydrocolloids are water-based impression materials that set by a sol gel mechanism. There are two types. Section 2.37.1 is on reversible hydrocolloids. Reversible hydrocolloid is derived from seaweed, is pleasant to use, and can be reused for casts and refractory casts. It's not dimensionally stable and should be poured immediately. Section 2.37.2 is on irreversible hydrocolloids. Irreversible hydrocolloid is also known as alginate. It's also derived from seaweed. It's easy and pleasant to use and is the most commonly used impression material. It's not dimensionally stable and should be poured immediately. Section 2.38 is on silicones. Silicone impression material is very accurate and easy to use, but it's expensive. It is used for fixed prosthetics, and that wraps up the provided text for this section. The same audiobook style. Elastomeric impression materials come as a two-part system, a base and an accelerator. Some brands supply the accelerator as a liquid. When mixed correctly, the material polymerizes into a rubbery mass. These materials can only be used once. They're used mostly for fixed prosthetics like crowns or onlays, though they can also be used as corrective liners for complete dentures and RPD bases. Never cross-mix pastes and accelerators from different brands, and handle them carefully. Some of these stains on clothes or towels are impossible to remove. There are four main types: polysulfides, silicones, polyvinyl siloxanes, and polyethers. Polysulfides are basically polysulfide rubber with fillers and pigments. One paste is usually dark and the other white, and they have a strong characteristic odor. You'll hear them called rubber base. Their low viscosity captures both hard and soft tissues very accurately, and they're used often in removable prosthodontics. Silicones, specifically condensation reaction silicones, are made of silicone and ethyl silicate. They shrink as they set, so use them in thin, uniform layers. They introduce the two-stage method, where a putty impression is made first and then a wash is done in that custom tray. They set translucent, smell milder than polysulfides, but need to be poured within 30 minutes because of dimensional change. Polyvinyl siloxanes, or addition silicones, are similar but more dimensionally stable. Shrinkage is controlled, so thickness is less critical. They're often used in two stages, very accurate, but pricey and fairly rigid. Polyethers use a polyether base and a sulfonic acid accelerator. They're among the most accurate, but set very stiff, making removal tricky in undercut areas and increasing the risk of breaking stone teeth when separating. Special characteristics. Polysulfides and condensation silicones should be poured within about 25 minutes. They aren't stable long term. Second pours lose some accuracy. Addition silicones and polyethers are dimensionally stable for up to 7 days, and second pours remain accurate. Polyethers absorb water, so minimize liquid exposure. Don't use them for dye plating. Addition silicones are hydrophobic, which makes bubble-free pours trickier. Now, impression plaster is specially compounded for intraoral use. It sets fast, is weak and brittle, so it fractures cleanly for removal from undercuts, and has very low setting expansion for accuracy. Soluble versions include cornstarch, so the impression can dissolve off with hot water. Hydrocolloids are water-based, capture undercuts elastically, and come in two types: reversible agar and irreversible alginate. Agar softens with heat, sets with cooling, and must be poured immediately. Alginate is a powder mixed with water, easy and pleasant, but also needs immediate pouring. Both are sensitive to water loss or gain, so timing is everything. Okay, picking up right where we left off. Section 2.38.2. Polyethers are highly hydrophilic, meaning they absorb water. So exposure to liquids should be kept to a minimum. They're not used in dye plating because water absorption leads to dimensional changes. Addition reaction silicones, on the other hand, are hydrophobic, which makes bubble-free pours more difficult. So extra care is needed to get a clean cast. Section 2.39 covers impression plaster. Impression plaster is specially formulated for use in the mouth. It has to set quickly to minimize chair time. Since it doesn't flex over undercuts, it has to be broken into pieces for removal and then reassembled. So it's intentionally weak and brittle to fracture cleanly and has very low setting expansion to preserve accuracy. Accelerators, retarders, and often color and flavor are added to get the right handling properties. Some impression plasters include cornstarch so they can be dissolved off a cast in hot water if a separator has been used, which helps prevent breaking the cast during separation. Section 240 is on hydrocolloids. In partial denture work, you need something that captures both tooth and soft tissue undercuts. Hydrocolloids deform elastically and rebound, making that possible. There are two kinds: reversible, known as agar, and irreversible, known as alginate. They serve similar purposes but are chemically different and need different handling. Agar softens with heat and stiffens with cooling, so it's reversible. Alginate sets by gelling when mixed with water and can't be reused. For reversible hydrocolloids, there are two types: impression and laboratory. The impression type is mostly agar and water, heated to thicken, then tempered and cooled in the mouth with about 70-degree water, then poured right away. It's great for RPD and fixed prosthodontic impressions, but can usually be poured only once because of evaporation and distortion. The lab duplicating type is stronger and can be reused if heated and stored properly, ideally in a double boiler that maintains water balance. Irreversible hydrocolloid, alginate, comes as a powder you mix with water. It's handy for RPD impressions, immediate dentures, and sometimes cast duplication. Work fast. Pour as soon as possible, within 10 minutes. Water balance is critical. Exposure to air or water changes dimensions. Some brands need a potassium sulfate fix to harden the cast surface. Always follow manufacturer instructions. Elastomeric materials covered earlier come as base and accelerator. Don't cross-mix brands. Handle carefully to avoid permanent stains. Use them once. Pours depend on material type. That finishes the provided text.